These are the notes for LT1, which is the start of our momentum and collisions unit. And the skill that you're trying to master in LT1 is to be able to calculate the momentum of an object. Food for thought. You don't need to write these down, but we will be discussing these in class. So which of the following has the most momentum? All right, a bullet fired from a gun, a semi-truck in a parking spot, a rabbit running through a field, or a bowling ball rolling down the alley. And we've talked about inertia in the previous unit. You remember, inertia was just based on mass. So an elephant versus a mouse. Didn't care who was moving, who was not moving. All we looked at is a resistance to changing its motion. So that depends only on mass. Things are a little different when we talk about momentum. So we'll come back to this. Momentum. You'll hear it referred to as inertia in motion. Okay, inertia in motion. This in motion part is perhaps the most important component of momentum, because what you're going to see, it's going to abbreviate it, is that momentum is the mass of an object multiplied by the velocity of an object. And the symbol for momentum is a lowercase p. I think every other letter was used already, like M is for mass, so they couldn't use that. They couldn't use a capital M because that has to do with a different formula we use later. So this is like some Latin word, impetus or something like that. But it's a lowercase p, and so it's equal to an object's mass multiplied by its velocity. So if we know that momentum has to have an object moving, because you can have the biggest number you can imagine, if you multiply that by 0, an object at rest, there is no momentum. That doesn't mean it doesn't have inertia. Okay, you can look at the high school itself, the building. The building has a ton of inertia. It weighs a lot, has a lot of mass, but it's not moving, no momentum. So if we go back to this, we've got a situation where, man, a bullet's little, but it's fast. Okay, so keep that in mind. Small mass, but a huge velocity. A semi-truck in a parking spot, really big mass, but it's in a parking spot, it's not moving. A lot of inertia, no momentum. A rabbit, rabbit has a little bit of mass. They're quick relative to us, but they're nowhere near the velocity of a speeding bullet. So yes, it has momentum, probably isn't going to win. Bowling ball, yeah, it has a decent amount of mass, but I don't know that anybody throws it even close to the speed of a bullet. So when we look at momentum, this little tiny bullet actually has the most of any of these things. Now if we just looked at inertia, we're looking at which one of these is the most massive. So a semi-truck has the most inertia, the bullet fired has the most momentum, because we have to factor in that velocity component. All right, so if there is no velocity, we have no momentum. You have to get really good at these symbols. Now the units. I know that everybody's a big fan of units of measurement in physics because they're not always straightforward, so there's some sarcasm. But usually the unit for mass is a kilogram. Sometimes it's a gram if it's a really small object. And then the unit for velocity is often a meter per second. So the units are these things swooshed together, a kilogram meters per second. Okay, that is the unit for momentum. And it's ugly, it looks strange. When it comes to solving calculations, it doesn't matter. It's not like it's anything you're going to have to type into Moodle. All right. So that's actually the concept behind this idea of calculating momentum. We take the mass of an object, we multiply it by its velocity. Hopefully you have one of these calculation sheets. If not, it's not the end of the world. Just look on here. But on your formula sheet, we'll need to write these varieties, I think. Yeah. Nope, never mind. I've already got it for you. So on your formula sheet, we know it's mass multiplied by velocity. So if you wanted to write it like this, you could. If we solve for velocity, it's momentum divided by mass. And if we were solving for mass, it's momentum divided by velocity. So all I did is just kind of rearrange those. write them out in a different form. All right, but you should already have those. So if we're looking for the momentum, that's our letter P, of a train car traveling at 143 meters per second with a mass of 2,030 kilograms, we're just going right to this formula up here. And I tend to keep these pretty simple, so you'll rarely, if ever, on a target solve for mass or velocity. When we do labs, we need these, but we're just going to leave it for now. So we know the momentum is mass times velocity. So we have a mass of 2,030 kilograms. We have to know kilograms is mass. We have to know that meters per second is velocity. So 2,030 multiplied by 143. So we go 2,030 multiplied by 143. And we get 290. That's just pure dumb luck right there. 290,290 units. Kilogram meters per second. Okay, this is all you would type into Moodle. Never put commas into Moodle, so just 290, 290. So that's the momentum of a train car. We have a little dog, a little 12 kilogram terrier. So there's our mass. There's the little guy's velocity. Looking for momentum. It's just mass times velocity. So 12 multiplied by 6 is 72 kilogram meters per second. All right, so those are pretty straightforward. But this next part here, if the momentum of an object is 250, a little dot there, my equation editor wasn't working on the Chromebook, so that's why I missed the little dot. If the momentum is 250 kilogram meters per second, and both mass and velocity are doubled, what is the new momentum? If you think back to the previous unit, we've done something like this before with mass and acceleration and force, that second law stuff. For this one, it's similar with just a little difference. And we'll add this to our notes. If you increase the mass of an object, we have a greater chance of having more momentum, assuming that the object is moving. So we know that that would be a directly proportional relationship. If we have less mass, we tend to have less momentum. Same thing for velocity. If something is moving faster, it definitely has more momentum. If something slows down, it definitely has less momentum. So we know that all of these things are directly proportional. Okay, they're both directly proportional. Mass relative to momentum as well as velocity. So when you do these problems, if mass goes up or down, the momentum must go up or down at the same rate. If velocity goes up or down, momentum must also go up or down at the same rate. So we write it out. Let's just deal with one at a time. Mass is doubled. So therefore, this momentum must go up to 500, 250 multiplied by 2. That's not the final answer, though, because the velocity is also doubled. So then we would have to multiply it by 2 again, and we would have 1,000 kilogram meters per second. Okay, so it's all based on that either mass goes up, velocity goes up, momentum must also go up. I'm going to skip number 4, let you try that one on your own. I've got a big number here in number 5. It doesn't matter. Okay, it's just 1,250,000. But it says velocity is doubled. Let's just start there before we even look at the mass. Velocity is doubled, which means we would also have to double this. Velocity goes up, momentum goes up. So we have 0, 0, 0, 0, 0. Why am I struggling? So it should be 2,500,000. I don't know. I'm struggling. Let me make sure that's the right one. 250, 0, 0, 0. Yeah, so 2,500,000. This next part, though, the mass is halved, cut in half. Remember, if mass goes down, momentum must also go down. So we're going to take that number, divide it by 2, and we end up right back where we started. So 1,250, okay, kilogram meters per second. So you would type that, 1,250,000 into Moodle. So that is the information for LT1, calculating momentum. Good luck.